Welcome to Breadboarding. In the previous couple of videos we've been adding the 16-bit EPROMs here, and this is what the system BIOS is going to go in eventually. But at the moment we've only been able to do very basic test software because at the moment we don't have any system RAM at all. And so what we're going to be doing during this series of videos is adding 32-bit system RAM, and we're going to be adding them on probably up to about 6 breadboards here, which we're going to need to try and fit towards the top of the board. So this is video 20 of the 386 Breadboard PC series, and in this video we're going to be looking at the 32-bit memory board and looking at the design aspects in particular. This is the PCB from the design that we've been basing this on. So there was an internal document published on archive.org with a lot of the internal design details for the D variant from December 1986. And you can see here we've got the 386 processor, the 32-bit memory board connector here, and there's also 32-bit power here. Now there aren't very many photos of the memory board around. I was able to find one here. So this is from the Vintage Computer Federation forums. It's a whole series of photos and things here from one of the members who was restoring a DeskPro 386-16. And you can see that this is where the connector plugs into the main motherboard. You can see that there are actually these plugs here actually plug into an expansion board, and there's 2 of these. So basically there's an expansion board that can plug over the top of this, and that expansion could do either 1 to 2 megabytes or 4 to 8 megabytes. And you can also see there's the power connector there. Now some of the other diagrams and things we've got access to, you can see here these are where the expansion board connectors are. So this plugs into the main PC, and this would come with the original DeskPro, but only half of the chips would be populated for 1 megabyte of RAM in the base DeskPro. And then this is the expansion board. So in this particular one, I think this is a 4 to 8 megabyte expansion board. So again, this would plug in over the top of the main memory board, and generally the first bank would be soldered, and the next bank here you would actually have socket to then plug in the expansion RAM. And this is the design document format. So you can see here that this block here on the main system board is soldered, and this one over here is all socketed. Now this is a diagram from one of the early reviews of the DeskPro. This comes from the PC Tech Journal. So this is one of the more detailed reviews, and you can see there was a photograph of the memory card there, but again that photo wasn't really very good quality in the way how the magazine been scanned. And this actually went through quite a lot of stuff and included some basic benchmarks at the end. So this was probably about 3 times faster than the PC AT at that particular time. And this diagram shows how the DeskPro actually allocated the memory. Now, although the 386 processor is capable of addressing up to 4 gigabytes of RAM, so that's a 32-bit address range. In fact, the DeskPro only came with the ability to decode 16 megabytes of it. Now, generally, the bottom 1 megabyte that the DeskPro would ship with would have the standard conventional memory that we'd have for MS-DOS, so 640K, but then it actually made use of the extra memory here to go at the very top of the memory map here, and this was to shadow the system BIOS, and also there was another 256K which could be used for the Compaq expanded memory manager or a virtual disk memory. And from 1 megabyte up to 10 megabytes, this was 32-bit expansion memory, so we could add another megabyte onto the main system board, and then you could add either another 1 to 2 megabyte expansion board or a 4 to 8 megabyte expansion board. So I'm going to be doing 2 megabytes initially, but I will be then looking at expanding it to 10 megabytes a lot later in the series, and we'll see whether or not that will allow us to install Windows 95 and some early versions of Linux. And it was also possible if you had older 16-bit memory cards, you could then fit those in, and those up to 4 megabytes of that. So back in 1986, 1 megabyte of RAM was quite a lot, and 10 megabytes was an enormous amount. If you just have a look at the costs of the DeskPro and how much memory cost in those days. So this was from the October US PC Magazine 1986, and there's the breakdown of all the price list here. So the Model 40, which was the base version with a 40 megabyte IDE hard drive and 1 megabyte of RAM, a 1.2 megabyte 5.25 inch floppy disk, and that had a base price of about $6,500. You then needed to add your EGA monitor and EGA card. If you then wanted to add another expansion card so that you could go up to 4 megabytes, then that was $849, and then the extra 1 megabyte was $549. Or if you're going, like we're going to be doing, and going for a full 10 megabytes, you'd add the 4 to 8 megabyte expansion card at $2,999, replacing these two here, and then you'd add another 4 megabytes of RAM, costing $2,699. So a 10 megabyte DeskPro 386 in 1986-87 would have cost you $14,000 in 1986 money, which I think is approximately 3 times that to get to modern day value. So it's about $42,000. So if you wanted a DeskPro with the full memory complement, it was going to cost a fortune. So just goes to show that the DeskPro was way ahead of its time, and only those with very deep pockets really could afford one of these. And the fact that 32-bit software routinely only became available around about 1990, so it's quite ahead of its time. And in the same magazine, I did find an advert which included the base dynamic RAMs. Now, these may have been different from the ones the Compaq required. The Compaq ones were a particular type, which I'll talk about, but 1 megabyte of 256K 100 nanosecond dynamic RAMs were $4.75. You'd need 36 of them because you've got 32 bits plus parity. So that would have been, even if you were just buying these ones, $171. And if you're looking at the 1 megabyte dynamic RAMs, then you'd need 72 of those. So even that would have been at least about $4,500, which is about $13,000 in 2026 terms. So to actually put more than about 1 or 2 megabytes of RAM in a PC of that era was very, very expensive. So this is a section out of the Compaq DeskPro technical guide, and it basically tells us how we can expand the memory, and we need to make sure that we load up the memory in a particular order, because if we leave gaps and things, then it will cause things not to work. So we can see that to start with, we have 1 megabyte with the standard soldered in memory there. Then we can add an extra 1 megabyte into the sockets onto that board. Then we're going to be adding the 8 megabyte expansion board, and that comes initially with the 4 megabytes soldered in, so that takes us up to 6, and then we can add another 4 megabytes in total to bring it up to 10. So to start with, we're just going to do the 2 green ones. So we're going to be doing 2 megabytes of RAM, and then these are the jumper settings and things that we need to set so that the DeskPro is able to detect what RAM it's got. So let's take a look at the original DeskPro design documents just to go through the high-level design. So I'll include the link to this PDF document that has all of these. We've been using this throughout the series so far. So this is the sheet 13 of the main system board, and what this has is the 32-bit memory socket. So that was the socket we showed at the bottom right-hand corner of the motherboard. And you can see here that we've got the full processor 32-bit data bus, so PD0 to 31, and we've got most of the address bus. We don't bother with 24 up to 30. We only include address line 31 and 23 downwards. Because we're dealing with 32-bit data, we don't have address lines A0 and A1 in dealing with the 32-bit memory board. And then these are all the various control signals, in particular the byte enable 3 to 0. In particular, the byte enable 3 to 0, this tells the memory card which of the bytes has actually got any valid data and is being updated. And we can see the rest of the memory signals here. So we've got the 32 megahertz clock. So this is the base clock going into the processor. Clock 16 is the main system clock, which is used for clocking most of the program or logic devices. The 32-bit memory expansion board will actually drive this line M32. This will go low when the memory board is handling the data. Now, the original memory board included parity, but we're not going to bother with parity because we're dealing with static RAMs, and we really don't need to worry too much about parity errors within our project. So this was the point at which the system memory board plugged in. So this is then the memory board. So this is the socket that goes into the main system board. And up here we've got some bidirectional buffers, but these particular chips are quite special in what they can also do is generate parity on saving, and they will check parity on reading. So these chips are a bit like bidirectional buffers that we've used elsewhere in the project, so the 74LS245, but they also have this parity checking as well. There's then some additional control logic down here that we'll go through as we do the board, but we need these additional control signals. But this section here is all to do with parity errors, so we're not going to bother with the parity errors there. And then this section has, the main section here is the address latches. So this is taking the processor address directly off the CPU and latching it. Now in the original design here, because it was using dynamic RAM, the dynamic RAM uses a sort of scheme called RAS and CAS, in which the address is effectively split into rows and columns, and so the chips themselves have half the number of address pins we'd normally expect for their particular capacity. And what happens is that the logic here generates a RAS strobe to tell it that it's got its row address, and then there's a later CAS strobe then gives it its column address. Now we don't need to worry about that because we're going to be using static RAM, and so there's also a section here as well, part of the speed improvements that the DeskPro included, in that there is a mode of the RAM that is used that if the row address doesn't change, then it means that it can just change the column more quickly. And these couple of chips here, comparators, basically would produce a signal coming out of here. You can see EQ1 and EQ2 should tell the logic over to the right hand side here whether or not the row address was the same as the previous request, in which case it could do a faster memory access. Then we've got this particular programmable logic device is actually responsible for generating the memory 32 signal, and it also takes some of the jumper settings and things to determine what it needs to enable for the memory 32, and you can see the jumper settings are down the bottom here. So we're going to be going with 640k and 1 megabyte of expanded memory to start with. And when we plug in the expansion memory, then whether it's a 2 megabyte or an 8 megabyte, then there are various signals here pulled low by those boards so that the hardware can detect what is installed. Then coming over here, we've actually got signals coming out here. So the byte select 0 to 3, this tells us which of the 32 bits are actually active. So in some cases, it might only be saving 1 byte or 2 bytes or all 4 bytes. And so the CPU will set these particular signals. These come from the byte enable signals from the CPU. And these are then combined with this AND gate with the memory read. So I think with the memory read, all of the outputs are enabled, but with the memory write, only those with the byte enable selected are actually enabled. And so we need to worry about this when we come to do some of the memory access logic rules. You'll see over here, there's then also the PLD for doing the row address strobe, and this handles some of the address decoding. So RS0 and RS1 are two of the main banks, so there's the bottom 640k plus the shadow area at the top of the system memory, and then I believe RS1 is then the 1 megabyte expansion RAM. And then these are the address multiplexers needed for the dynamic RAM. So as we've said already, because we're using static RAM, we don't need to worry about multiplexing the address lines. So the memory board includes a configuration register, and in particular this allows us to write protect the top area of RAM to stop it being overwritten, and it also allows us to copy the system ROM into this area and then write protect it. So as part of the Compaq BIOS, then as it was powering up, it would undo the write protect for the top area of memory, copy the ROM in there, and then write protect it. And so this particular register is actually used, and it's actually mapped to the 80C00000. So this is sort of up in the top 2 gigabytes of address space. So it's the only time that the address line 31 gets used is whether or not we're dealing with this particular system memory board register, and I think also for any maths coprocessor may use the upper address line for memory select for that. So then we have a register here that allows us to read some of the jumper settings. So the jumper settings here for the memory configuration, and if we were using parity, then it would actually allow us to read the parity errors. And then up here we have the main control PLD. So this produces a lot of the control signals. So the column address strobe and the row address strobe output and the memory read, memory write. So a lot of the control signals come out of there. This bit here we don't need to worry about. This is where we're dealing with the comparator output to tell us whether or not we can do one of these fast reads or not. Again, all the reads can potentially be fast because we're using RAM that is faster than the original dynamic RAM. This section here is to do with the parity, so whether or not there is a parity error, so we can ignore that. And this section here is part of the decoding of the RS0, RS1 and the CAS and RAS lines into the different banks of RAM. And because for our 2 megabytes of RAM that we're going to be doing, we're only really going to be having the byte level enables that we need to worry about. So whether we're writing to byte 0, 1, 2 or 3, the rest of the RAS side of things we don't need to worry about. So again, this logic here will be included in some PLDs. So this is then one of about 4 or 5 memory boards. So this particular memory board has some buffers here to drive the RAM. So you can see here that for one bank here, we've actually got 8 bits for 0 to 7, and there's parity. So this is parity 0. So this is for the sort of byte 0 of the memory here. So this will be the RAM, and then these will be sockets. So these are empty. And these buffers here, and there's some resistors to prevent spikes through these resistor values here. And in fact, when you look at the other sheets, I haven't copied them all here, but on sheet 5 we've got CAS 0 and RAS 0A, and we've got CAS 1, 0A and 1A, and we've got CAS 2 and CAS 3. So you can just see that each of the sheets basically is for byte 0, 1, 2 and 3. And then this is the connector for the expansion board. So these are the 2 connectors that we looked at the left and right hand side of the board. And so you've basically got the data lines here, address lines, and some of the control signals here. Now the original internal design document doesn't include the design for the 4 to 8 megabyte expansion RAM. So this actually comes from the original DeskPro technical guide. So this shows the expansion board. So you can see here that we've got the 2 connectors that plugged into the 2 sockets from the previous page here. The 2 sockets there. And then we've got up to about 7 pages. I believe the reference in the bottom here doesn't necessarily tie up with the references appearing on here. I think there's one out on some of these references when we look at it. So obviously we've got all the decoupling capacitors. Now these buffers here are actually just used to provide the parity values for the upper 4 megabytes of expansion RAM when there's no RAM installed. So this will only be enabled when there's no block 1. So you see down the bottom here, there's no block 1. So we can ignore that. So then we've got a decoding PLD. Now we don't have the rules for this particular one, but basically what it's doing is taking the byte enables 0 to 3, and it's taking the various control lines, address lines, and working out what values we need here. Again, we don't have to decode all this sort of stuff. What I'm going to do is to do this decoding in a couple of PLDs. Then these are the banks of the RAM. So you can see here similarly that these are 1 megabit dynamic RAMs, so slightly more pins. So the goes up to an address 9 pin. And you can see the RAS and CAS coming in here. Now the data in and the data out are just wired together with these dynamic RAMs. So there's no difference between in and out, but we don't need to worry about this. Although if we get up to 10 megabytes of RAM, we will have 20 static RAM chips, but I don't believe we should need any additional buffering for that. So then these are the other ones. You can see that we're just on the different banks, and some of these additional signals down here are slightly different. And then this is the socket that actually plugs into the base system board. And what you can see here, there are actually 2 pins here. This pin here is to do with a 2 megabyte board, and this pin here is the 8 megabyte board, but the 8 megabyte board ties this one to low and this one to low. There are pull-up resistors on the main system memory board such that if the memory board was not plugged in here, then these would be high. So by pulling these low, this is how the rest of the memory board knows that we've got an expansion RAM here. So just to recap, this is the CPU and the 32-bit memory connector and the power connector, and then these were the two expansion connectors here. Now I don't have any photos of the 4 to 8 megabyte expansion board, but that would plug in over here. So I have updated the main KiCad diagram that I did for the original DeskPro design. I haven't included the 4 to 8 megabyte expansion card in that design. So this is the copy of the design documentation I put into KiCad, and you can see up here we have the 32-bit memory connector, the memory decoder and multiplexers, the driving of the RAS and CAS. Now I've only included one RAM chip here because putting in 72 RAM chips was not actually going to be very constructive. So there is this here. The links for this will be in the URL below, and this is in my GitHub repository. But I've used this to then update the main KiCad diagram for the Breadboard PC, because this reflects the original DeskPro design, whereas the Breadboard PC design actually reflects the design we're going to be using. So you can see this is the section that we were doing. So this is the ROM section that we've been doing over the last number of videos. And now this section at the top here is actually the 32-bit memory card. See what you can see here, we've actually got 4 512K static RAMs. So these have got about a 55 nanosecond access time. So these are much faster than the original dynamic RAM chips. And since the processor at the moment is running at half the speed the original DeskPro ran at, we shouldn't have any memory timing issues to start with. So let's take a look at the overall design. So you can see here, this is the processor, and down here we have the processor data bus. So you can see it's coming out here and onto this side of these latches over here. Then we're feeding into these buffers, which we'll talk about the buffers in a few minutes. We've got the byte 0 going PD0 to PD7. So this is talking to this first chip. This is the buffer that we use to read the various sort of jumpers, so the memory configuration jumpers, and also if we're using the parity, then this would also bring the parity error information. At the moment that's just tied to 5 volts. Then we've got the byte 1, so that's PD8 all the way up to PD15. Byte 2, which is PD16 all the way up to PD23. And then we've got byte 3, which is PD24 up to PD31. This goes to this chip as well. I should probably just mention that there are these 4 chips here, and these are doing all of the signals to do the chip enables, one for each chip. Now the reason why I've got one of these for each of these chips is that you'll notice here that we've also got, in addition to chip enable block 0, 0, we've got 0, 1, 0, 2, 0, 3 and 0, 4. And this is to allow for the expansion of the memory from 2 megabytes up to 10 megabytes a lot later on in the series. And the way I'm going to do this is I'm going to build some expansion connectors out of strip board and a number of sockets and connectors to basically allow up to 5 chips to piggyback off this one location here. And all we need to do is to allow for each chip to have a different chip enable. And so I've worked out a way how to do that. So by putting these chips in here, it basically means that we should actually just be able to swap out these single RAM chips for my 5 chip sort of RAM sandwich, and then we should then be able to just hook this up. You can see over here we've got the bus address 31, just helps us to distinguish when we're talking to the RAM and when we're talking to the configuration port for the RAM. And we've then got the address 23, 22, 21, and that's enough to divide up the upper 16 megabytes of RAM into 2 megabyte blocks. Then we've got the RAS and CAS signals, and RS0 and RS1 come out of the other PLDs to enable either the lower 640 and the top shadow RAM, and RS1 I think is the 1 megabyte of expansion RAM. Coming in here we have a chip select, and there's 3 chip selects, and we'll talk about those in a minute. So these 4 chips here provide the chip enables down here, and I'll be talking about the other signals that we use for the RAM a little bit later. Then we've also got the addresses, so processor addresses coming out of here. So as I said, we've already got 31 and then 23 going all the way down to 2. And as I mentioned earlier, the reason why we don't have PA1 and PA0 is because these byte enable lines effectively tell us for the 32 bits or 4 bytes of data that we're reading at a time, which byte is actually enabled at a time. So if we're reading all 4 bytes, all these 4 lines will be 0 at a time. If we're just reading 8 bits for the lowest byte, then 3, 2 and 1 would be high and BE0 would be low. Then up here, the logic that I showed you on one of the first slides, there's a number of gates and things needed to provide that sort of logic there. There's also down here, this is the part that actually conditions the byte enable signals. These byte enable signals are combined with the memory read, and then coming out of here are these chip selects. The chip select 0 to 3 basically says that we're either reading a particular block or we're writing a particular block. Now when we're reading, all 4 will be enabled. When we're writing, only the specific bytes that the processor identifies from the byte enables will be enabled. And these are the lines that go into each one of these. So this is 0, 1, 2 and 3, 0, 1, 2 and 3. Then we've got a couple of PLDs. So this one here is responsible for generating the memory 32 signal. So this basically tells the rest of the system. So when the memory 32 signal comes all the way down here, then memory 32 coming to these signals here basically tells all this logic down here that you're not doing anything with this particular request. It's all going to be handled by the 32-bit memory board. So what this PLD does here is it takes in all of these address lines, takes in some of the memory configuration options. Now for the moment, I haven't got jumpers here. I'm just going to be wiring these into the configuration that we're going to use. So we're going to have the 1 megabyte expansion RAM enabled, 640K system RAM. And for the moment, the 8 megabytes is going to be disabled. We will change that to be low when we add the extra RAM later in the series. So these are all of the address buffers, and we also buffer the byte enables as well. And these are actually all latched. So you can see here the C lat here. That latch basically latches all of the addresses from the CPU at a specific cycle. And what that allows the CPU to do is, by signaling the next address to the CPU, means that the CPU can start getting ready the next address because we've saved the one that we need to work with. And so the processor can go off and start working on the next address. And we've got 2 other PLDs here. So the control PLD, this is actually what generates most of the control signals. So you can see that the memory read, the memory write, memory ready, the CAS and the RAS signals. So these are all the timing sensitive signals needed to generate all of these enable signals over here. And obviously in the original DeskPro, because the RAM chips didn't have a specific chip enable, it just used a combination of the RAS and CAS together. Effectively was the chip enable. And then this RAS PLD over here actually generates the write enable signal, the write protect signal, which is used in controlling the access to the register, which controls whether we can write protect the upper area of RAM, which is used to shadow the BIOS, and also generates the read and write enable signals for the port, which is used for configuring the RAM. And for the moment, you can see here the hit is the input from the 2 comparators that tells us whether we're dealing with the same row. Now for the moment, I'm going to be wiring that to 5 volts, so that will mean that it's always saying that it hasn't got the same row, and at some point in time in testing we'll change that to be low, and that should actually speed up all the memory accesses. Because we're running the processor initially at half the speed, the original DeskPro, I wouldn't expect to be any timing issues, but what we should then be able to do is when we speed things up, we should be able to change that to be low, and again we would expect that to be a little bit faster. So a few signals here which are then going off to the rest of the board down here. So rather than having lots of lines going all the way down to the bottom here, you can see that sort of memory I/O and things like that is connected all the way up here, as is these other control signals. Then we've got the configuration rules for the chip enables. So if you just look at byte 0 first of all, we're looking at block 0 first of all. So you can see for byte 0 we've got the RAS combined with either RS0 or RS1. So this is the lowest 640K and the upper shadow RAM area, or the 1 megabyte of expanded memory, CAS and CS0. So CS0 is coming from these signals from down here. Similarly, byte 1, we've got the same apart from CS1, byte 2, the same apart from CS2, byte 3, the same apart from CS3. And then when we start to look at the later blocks, so byte 0 for block 1, 2, 3 and 4, then obviously these address rules will then be replaced in the RS0 and RS1, but we'll deal with those a little bit later in the project. And all of the control signals for the RAM, there is the write enable. You can see WE0 write enable comes from the PLD here, and then the read signal is MRD. And this is actually used to do the output enable on the chips, and is also used to actually control the direction of our buffers. So just a few more things to cover. So this is my version of the memory map. So you can see here the bottom 640K of RAM. So this will be the RS0. It's actually covered by this, this and this, and then the RS1 is covered by this. And then when we actually add the extra memory, then those additional chip enables that I showed you and those PLD chips will actually do the block 1, 2, 3 and 4. So block 0 is all we're dealing with to start with. So we'll refer back to the block diagram from time to time, but the main thing really here is our 32-bit memory card does not involve any of the legacy 16-bit PCAT type bus. So we're just dealing strictly with the processor address bus PA2 up to PA31 and the processor data bus PD0 to PD31. And in fact, some of the documentation in the memory card, so there's an entire section in the DeskPro technical guide on the memory. You'll see here, this is where all this comes from, so all the details about the ROM mapping and how all of the memory is configured, and also schematics actually come from this section. And I've just pulled out a few bits. So the key thing really here is there are no I/O related signals that exist on the memory expansion bus. So none of the I/O appears on the 32-bit memory bus. And also the memory expansion bus limits the addressing of physical memory to 16 megabytes. The PA31 signal on the bus addresses special memory map registers in the DeskPro memory board, which we've covered. But also it does actually allow the very top area of memory to shadow the system BIOS and to be used for the Compaq expanded memory manager. But also an important thing, the 32-bit bus cycles do not appear on the 8 and 16-bit bus. So for example, if people had legacy 16-bit debug cards, for example, then you wouldn't have been able to use that to debug the Compaq DeskPro because all the 32-bit memory accesses would not appear on there. And as we've already said, the M32 active low signal indicates whether or not the 32-bit board is actually handling current request and whether all the system board should leave everything alone. Now, one of the simplifications in ignoring parity, the 74F657 chips, which is a rather unusual one I've not come across, but you can see here it has a few more pins than our normal bidirectional buffer. The normal bidirectional buffer has 20 pins and this has 24, and the reason for that, it has parity error and the parity calculated output, and also whether or not we want odd or even parity. And the input here, the transmit receive, so when it's low we've got B to A, and when it's high we've got A to B, and the direction on the buffer here is equivalent of the DIR. So in fact, when DIR is low we've got B going to A, when this is low we've got B going to A. So in fact we should just be able to replace these 657s with the 245s without any trouble. And it's also worthwhile just having a quick look at the data sheet for the dynamic RAMs. So this is a Hitachi datasheet, and these particular RAMs include the high-speed page mode capability. So this was something that the DeskPro made use of, so that when only the row address was changing, so this meant that if data was being accessed in a 2K block, then the row address would not have to change, and it would mean that the memory accesses would be quite a bit faster. And it also shows here that we've only actually got address pins going up to A8 here, even though for 256K of RAM, you would obviously need more than 8 address lines. And contained within here are the various timing diagrams, which I've got copies of, and we'll go and have a quick look at that. So in trying to work out how to change the decoding of the various signals, so I'm working out how to handle the outputs here. So this was providing RAS and CAS outputs to all the various banks of memory. So I needed to work out how that actually worked. Now, in fact, when you look at these timing diagrams, you can see that RAS is actually going low for quite a long time. Then CAS goes low just for the last half of the cycle, and that the data will be read towards the end of this CAS period. And then on the right, we've again got RAS goes low first, then CAS, and then the write enable goes low here. So in trying to work out how to map these things, then generally we want to have both RAS and CAS low when we're actually doing the read, and we'll have RAS and CAS low and write enable low when we're doing the write. So in looking at the chips that we're replacing this with, so this is a chip which is the 512K static RAM, and you can see here the address lines go up to A18, which allows us up to 512K. And we have 3 control lines here. So write enable is fairly straightforward. Write enable was wired to memory write, or the WE0 on the actual memory card. Output enable is actually used for the memory read control line. So again, this is fairly straightforward. The output enable will go to the memory read active low on the memory card. But the chip enable here was not quite so straightforward. So the chip enable doesn't exist on the dynamic RAMs because it makes use of the RAS and CAS together, effectively make up the chip enable. So this is where these rules that we had to combine the RS0, RS1, RAS, CAS, and also our byte enable signals, those rules all came out of this. So there's probably enough there of detail to go through. I didn't want to then start trying to lay out the boards during this video because there's going to be way too much to cover. So this basically shows how I've managed to adapt the design for the 32-bit system board, and the expansion board has been incorporated in here. The only tricky bit's going to be making these sort of piggyback static RAM stacks here. So I've got some sockets and things. I can build a 5-high piggyback connector to go over these. So hopefully when we come to do our 10 megabytes of RAM, that will work. So if you don't want to miss out on future videos in the series, please hit subscribe. If you could hit like as well if you found the content interesting, it just helps to make the videos available to more people. If you'd like to leave comments below, I do try and get back to you within a day or so. Thanks for watching.